half x minus 3 halves. So let's plug these on here and see that this here will graphically tell me it's correct. Alright. We'll plug this in here, so that's about 3. When we make this equal 0, we get negative 3 halves. So let's sketch that. Let's see if I can get that to be where I want it to go. I'll make it a little bit longer. Alright, so we've sketched our first function up there. It's a straight line 1 to 1. Let's sketch the second one. So negative 3 halves, so negative 3 halves here, and we're at 3, so let's put 3 here. So if we make this equal to 0, when x equals 0, we get, or y equals 0, we get 3. Yeah. So let's now sketch this one. Look what we're noticing. Look what we are noticing just here. If we use our green line, we should notice that these two are reflections of each other. Okay? We're reflecting each of these functions. So our original function and our inverse function are reflecting on top of each other in terms of the points of intersection. What's another thing that we notice when we look at this here? Well, we notice that these 2 points, the x and y points, they're switched. And that's going to happen because we're switching the x and y. But what else happens here is, well, the domain for this one was negative, or in this case, the x coordinates, and this one was negative 3 halves. Okay? The y coordinate was 3, or the intercept. Here, the y-intercept is negative 3 halves, and the x-intercept was 3. So they're basically switching each other. And we can now determine a rule from that. And that rule that we can determine from this is, we can state that the domain of f of x is equal to the range of the inverse. Okay? And we can also state that the range of the range, not can't try and compare that, the range of f of x is equal to the domain of our inverse. And this here is an important rule to have. Really, really, really important. It's not a property in such of the 4 properties I'm talking about, but it's something that you should have an understanding about. So we looked at the 3 different ways of, or three of the 4 different properties that determine if something is an inverse. The last one is basically the visual representation of what this is happening here. And that last one here is that, and we'll write it here now, the composition of f of x and its inverse will always equal x. Composition, remember that's the composite functions that we looked at a little bit earlier. So let's test this and see if that works. So if we're looking at this part, let's test that composite function. So what do I mean by composite function? Well, if I had f of f here, that should equal x. And if I had my inverse function with a composite of a function, that should also equal x. And that should line up with this, where y equals x, according to our reflection of our graph. So let's put that into practice. So we've got, in this case, we'll just change this here to f of x. So let's put that data in. So if we have f of f minus 1 of x, we can rewrite this here as f of half x minus 3 halves. So if we're going to be doing that here, we're going to substitute this into this function. So we get 2 brackets, half x minus 3 halves plus 3. Well, 2 times a half equals a 1, so I'm just left with x. 2 times this is minus 3, plus 3 is equal to x. So that's correct. We've worked out the first part is correct. If we look at the second part, where we're going to have, where this here is the same as writing 2x plus 3, let's toggle that in. So this here is going to equal half. Remember, we're replacing the x, so 2x plus 3 minus, 3 halves. So let's work this out here again. We're going to get half times this is going to be an x. Half times 3 is 3 halves, so x plus 3 halves minus 3 halves. Those will cancel out, so I'm left with x. And that is the fourth property when it comes to inverse functions. So when we're looking at the inverse functions, we're looking to see if we have properties that satisfy that. 1-to-1. It passes the vertical and the horizontal line test. We can graphically represent it. So this here is the graphical representation of all this. Okay, and the last one here, which is a non-standard one that we don't put in there, is that the domain and the range are reflective of each other. And the last one here is that the composition of your function and its inverse will always equal x. Now, I wouldn't strongly agree to graphing everything all the time. If I had 2 functions and I inversed them, I wanted to test if they were actually real inverse functions, I'd use the algebraic test. And the reason why I'd use the algebraic test is because I'm going to get that exact answer. Where graphing it, you have some ideas of scrutiny there. You may make an error in graphing it. But with the algebra, you've got all that work there. You know how to use composite functions. You can see, okay, well, this equals x, but this one doesn't equal x. So therefore, they're not ideally inverse of each other. So inverse functions, really powerful tool to use. We can use this a lot when it comes into high level of mathematics, into integration, okay? But we are looking at the 4 different ways of inverse functions, how they work. And we've looked at the 4 here: 1-to-1, passes, reflective, composition. And don't forget, when we're looking at the domain of f of x is the range of the inverse, and the range of the function is the domain of the inverse. See you next time.